Good day to everyone. Today we're from Group 4 with me, Suryo Mentaram, and my group mate, Zaky, Arisyi, Fakhry. We are going to presentate about the problems related to statistical process control and process capability for our midterm test, UTS Penilaian Kinerja Manufaktur. Okay. Question 6.25. The accounts receivable department at Wing Manufacturing has been having difficulty getting customers to pay the full amount of their bills. Many customers complain that the bills are not correct and do not reflect the materials that arrive at their receiving docks. The department has decided to implement SPC in its billing process to set up control charts. 10 samples of 50 bills each were taken over a month's time, and the items on the bills checked against the bill of lading sent by the company shipping department to determine the number of bills that were not correct. The results were tabulated. So the first question, part A, determine the value of P bar, the mean fraction defective, then determine control limits for the P chart using a 99.73% confidence level 3 standard deviation. Has this process been in control? If not, which samples were out of control? Part B is how might you use the qualitative tools discussed in Chapter 6 to determine the source of the billing defects and where you might start your improvement effort to eliminate causes. Okay. For Part A, value of P bar, mean fraction defective, P bar equals to total number of defects divided by sample size times number of samples. So it is already mentioned that the sample size is 50, the number of sample is 10, and the total number of defects we can count from the previous table. The total is 47. So 47 divided by 50 times 10 equals to 0.094. Then we can calculate the standard deviation of the sampling distribution. Sigma p equals to square root of p times 1 minus p over n. N is the number of samples again. So P bar is 0.094 times 1 minus 0.094 divided by 50 equals to 0.0041270.813. Number of standard deviation Z equals 3 for 99.73% confidence level. Then we can calculate the upper control limits UCL and equals to P bar plus Z times sigma P, and the lower control limits LCL equals to P bar minus Z times sigma P. Then we tabulate the total number of defects, the sample size, the number of samples, and the number of standard deviation is 47, 50, 10, and 3. We get the values of P bar 0.094, sigma P 0.041271, upper control limits 0.217812, and the lower control limits minus 0.02981. But there is no negative value for our control limit, so we consider LCL as 0. Then using Minitab 17 to construct the P chart, you can see here, this is the P chart, this is the P bar, this is the upper control limits, and this is the lower control limits taken as 0. The upper control limits, as we calculated before, is 0.2178. So a P chart is an attribute control chart used with data collected in subgroups of varying size. The process is considered not in control if the proportion of samples is higher than the upper control limit of 0.2178. We can see that it is not in control at sample number 3 because it is above the UCL. And the Minitab also said that the test result for P chart of number of incorrect tests. We see here 1 point more than 3 standard deviation from center line. Test failed at points number 3. For part B, The total quality management emphasizes on excellence in all aspects of products and services. We can use several TQM tools out of the 7 tools. So first, using the cause and effect diagram, or as known as the fishbone diagram, we can start by brainstorming what are the possible causes that results in the billing defects. So we put the cause in the bones, and then the head of the fish is the problem, and we can ask several levels of why until we could identify the root problem. Next, we could use the Pareto chart by applying the Pareto principle. 80% of a firm's problem are a result of only 20% of the causes. We choose the possible causes of billing defects from the previous cause and effect diagram. Then we identify the highest number of occurrences for the cause. The majority of the defect bills could be eliminated when this one cause is corrected, as stated by the Pareto principle.
Okay, so now we're going to talk about question 6.43. It reads, the specifications for a plastic liner for concrete highway projects calls for a thickness of 3.0 millimeters plus minus zero point 0.1 millimeters. The standard deviation of the process is estimated to be 0.02 millimeters. So the first question is, what are the upper and lower specification limits for this product? Number two, the process is known to operate at a mean thickness of 3.0 millimeters. What is the CPK for this process? And the third question is, about what percentage of all units of this liner will meet specifications? So let's take a look at the first question. What are the upper and lower specification limits for this product? Now we see that it's already stated that the specifications calls for a thickness of 3.0 millimeters plus minus zero point 0.1 millimeters. So to find the upper and lower specifications, all we have to do is just get the base value, which is 3.0 millimeters, and the lower value will be minus that of the zero point 0.1 millimeter and upper being plus of the 0.1 millimeter. So we get that LSL is equal to 2.9 millimeters and USL is equal to 3.1 millimeters. And so that's the answer to the first question. Second question is, the process is known to operate at a mean thickness of 3.0 millimeters. What is the CPK for this process? So what they've done is given us the mean thickness. And now we have to find CPK. Well, first of all, what is CPK? CPK is process capability. It basically represents the performance level of the process after it has been through a statistical control. So they measure CPK by first getting the value of CP, CPU, and CPL. CP is also process capability, but does not take into account the centralization process. CPU is the process capability based on upper specification limits, and CPL is the process capability based on the lower specification limits. So what this is saying is data can sometimes have a data it can sometimes lean more towards a lower or upper specification limit. It's not always going to center around the middle. So what CPK calculates is that it's taking into account where the process is centered. And CPK is used to determine if the process is capable of meeting specifications. So if the CP tells us the process capability, what CPK does is it provides a centralizing factor to it. So just in this slide, before we get the answer, I would just like to point out two different diagrams. These are basically how to read the CPK curve or CPK diagram. In the left, you can see what happens when CP and CPK deviate. If CP is lesser than CPK, then it will tend more towards the left. It will, and the opposite being that it will shift more towards the right. However, if the CP and CPK is equal to one another, that means its mean will be exactly in the midpoint, and the curve will be perfectly centralized to the midpoint. And the second figure on the right shows the overall size of value of CPK. We see that as the CPK gets larger, the curve gets more defined or more thinner. So we can see that the CPK of 0.5 is very stretched out, and there's a 13.4 approximation fallout, meaning there are errors. There are products that exist outside of the boundary. Whereas the other extreme version of it, which is a CPK of 10, is completely centralized and has an approximation fallout of uh, less than 0.0000001%. So what this is saying is that the larger the CPK value is, the less likely it has items outside of the specification limits. So what we're looking for is a very well-defined graph. So we see that this is our answer right here after calculating CPL and CPU. CPL is equal to the mean minus the LSL divided by 3 times the standard deviation. CPU is equal to the USL minus mean over 3 times standard deviation. And the both of them, also including CP, has a value of 1.7. So we can see from the very top that it's outlining every single value we have or we have found. The specification, which is of course 3 millimeters plus minus 0.1 millimeter, LSL 2.9, USL 3.1, mean 3.0 millimeters, standard deviation being 0.02 millimeters, CP, CPL, CPU, and CPK all having 1.7. And you can see from the curve diagram that it's perfectly centralized. It has the same distance from LSL to the mean mean to the USL, meaning that it's a very good definition of centralization. So that's the answer to number 2. We'll see the third and final question, which is asking about what percentage of all units of this liner will meet specifications. So technically what this is asking is how much percentage or how many percent will the answers that we have gotten, how much will it be a representation of the units within the specification limits? And the answer to that is that each specification limit lies 5 times the standard deviation from the central line. So practically, it's 100% of all units will meet specifications. We can see from the curves before, a 1.33 value of CPK is already very highly, is very good with very minimum errors. And we have a 1.7 value, which is even better. And usually these follow a 4 sigma or 4 standard deviation standardization process. And we have an answer that has a 5 times standard deviation. So it's even more precise. So theoretically speaking, 100% of all the units will meet specifications. And yeah, that's the answer to number 3. This is our reference page. This is where we have the questions and other sites that we've studied and researched. Thank you for listening.